All right, sorry I had to cut that last video short. I had something come up and I had to stop, but we're going to pick this up where we left off. So what we had done at the end of that first video was we used the test point of 0, and we found that by plugging that into our derivative, we got something negative. So here, f prime of x will be negative. It's going to be less than 0. On this subinterval, I need to pick any number greater than 9. Pick something ridiculous if you want. Pick a billion. Right? If I plug a billion in for all of these x's, then either adding 5 or subtracting 9 is not going to make that negative. So no matter what, I have positive times positive times positive, which is positive. F prime of x will be positive here. So here's what this is telling us. The function is increasing on the following intervals. Negative infinity to negative 5. And 9 to infinity, because those are the intervals on which the derivative is positive. Now, somebody will probably end up asking me this, so I'm just going to answer this now. Why am I using open parentheses as opposed to closed brackets? Well, you know, first of all, you can never use a closed bracket around infinity or negative infinity because those are not numbers, they don't exist, so we always use open parentheses there. But this is an open parenthesis at negative 5, and this is an open parenthesis at 9, because we do not want to include negative 5 and 9 in these intervals. And the reason for that is because the derivative is neither positive nor negative at those numbers. We already found that it's equal to 0 there. So the function is neither decreasing nor increasing at those values. Those do not belong in the intervals. We are decreasing on the interval negative 5 to 9 because that's where my derivative is negative. Okay, so that's how I'm going to use that increasing decreasing test. All right, now this concept leads to something very, very useful. It leads to a test or a technique, one of two that we're going to talk about, for finding local extrema, local maximum and local minimum values. So first of all, let's see, I'm using the term critical number there. Did I define that already? I can't remember if that was defined in a previous section or not. Let's see. Oh, yes, we did. We defined critical number previously. All right. I don't need to talk about that again. So let's suppose that C is a critical number of a continuous function f. And remember, critical number means one of two things. It's a place where the derivative of a function is either equal to 0 or does not exist. Okay, so if this is the case, C is a critical number of a continuous function f. If f prime changes from positive to negative at that number, then f has a local maximum at C. If the reverse of that happens, if f prime changes from negative to positive at C, then f has a local minimum at C. And if f prime is positive to the left and right of C or negative to the left and right of C, meaning there's no change from positive to negative or vice versa, then f does not have a local maximum or minimum at C. Now, we don't need a proof of this because this is an immediate consequence of the previous theorem we just talked about, the increasing decreasing test, and these graphs illustrate why that's the case. So first of all, look at this upside down parabola that we have here. At the vertex of that parabola, we have a critical number because the tangent line there would be horizontal. That's a place where the derivative of this function would be 0. And just looking at the graph, I can see that the derivative to the left of C should be positive because I can see that the function is increasing there. Okay, this tangent line would have a positive slope. As I move to the right of C, my function goes from increasing to decreasing, which is where the f prime would be negative. And according to the first derivative test, when f prime changes from positive to negative, we have a local maximum, which is clear from this graph that that is a local maximum. It's the highest point that I can see on this portion of this graph. So that makes sense because if a function is increasing and increasing and increasing up to that critical number and then decreases away from that, it could not have gone any higher than that critical number because after that, it's decreasing. So that logically would have to be a local maximum. The local minimum is the reverse case of that, and it follows the same logic. Here, I have a parabola where the vertex is a local minimum. It's the lowest point. And I can see as I move from left to right that we are decreasing we hit that critical number, and then we increase away from it. That's going to decrease to a minimum and then increase away. So that means, that confirms part B of this. Part C and D, these two graphs here, or graphs C and D here, correspond to part C of the first derivative test. Here I have a critical number. This looks like a cubic function. So there is a place right here where the derivative is equal to 0, but we're increasing up to that number. We hit that place where where f prime equals 0, and then we increase again away from it. So because I increase up to this point, but then increase away from it, we're reaching even higher points over here. So this couldn't be a maximum, and similar reasoning would say it also couldn't be a minimum. We can see from the graph that neither is the case. Here's a similar example over here. So this is sort of illustrating why the first derivative test works. Okay, so let's do an example that right here we're using the exact same example that we did here. Okay, but what I'm going to do is use my previous work. So again, we are looking for where the derivative of this function changes from positive to negative or from negative to positive, because the first derivative test will give us either a maximum or a minimum in those cases. Okay, here we go. So rather than rewrite all of this stuff, let's come back here. Okay, f prime of x is greater than 0 here, and it's less than 0 here. Now it's easy to forget which is which in the first derivative test. So here's what I like to do. At the place where the first derivative is greater than 0, we know that that means our function is increasing. Okay, then we know that this is a critical number, so we should have a horizontal tangent here. And then we end up with on this interval from -5 to 9, a place where the derivative is negative. That means our function should be decreasing. So the graph of my function is going to have something resembling this. Increasing, hits a critical number, decreases. I can see that there is a maximum there. Okay? Similarly, we're decreasing in this interval. We hit another critical number, 9, and then we increase away from it because our derivative is positive. So I'm going to have something resembling that. Okay? I can see that at x equals -5, I have a local maximum, and at x equals 9, I have a local minimum. Okay? Now remember, those are not the maximum and minimum values. Those are the values at which maximum and minimums occur. So I have, let's write this again. What did I say? -5 is a maximum. We have a local maximum at x equals -5. But what exactly is that local maximum equal to? Well, we would have to plug that in to this function right here to determine that. So of f of -5, which is equal to -5 cubed minus 6 times -5 squared minus 135 times -5. And I'm just realizing now I didn't work this out ahead of time, so I'm going to have to work this out here. That's equal to -125. That's 25 times 6, which is 150, so that's minus 150, plus, what is 135 times 5? I wish I would have worked this out ahead of time. That's equal to, what is that? I'm going to do this old school. 135 times 5, 25, 17, 675. Okay, so let's see, that's going to be 75. We'll subtract that away. This should be equal to 400. We have a local maximum of 400. Okay, I'm going to be embarrassed if I got that wrong. That's all right. Minimum. Our local minimum occurs where? At x equals 9. We confirmed that on the previous page. So f of 9 is equal to 9 cubed minus 6 times 9 squared minus 135 times 9. Let's see if we can do this in a smarter way. I'm going to factor a 9 out of all of this, since I have to do this mentally now. That'll leave me with a 9 squared, which is 81, minus 6 times 9, which is 54, minus 135. What's that? All right, so we've got, let's add these. This is going to be 9 times 81 minus 189, which equals 9 times negative 108, which is equal to negative 972. Okay, once again, I'm going to be embarrassed if I got that wrong. I'll check that later. But sometimes you find yourself without a calculator and you got to rely on your old arithmetic abilities. So hopefully mine are not too rusty. I believe we have these right, but I'll check that later. All right. So these are our maximum and minimum values, or local maximum and local minimum values, I should say, for that function. Okay. We're going to do another example. We want to find the local maximum and minimum values of f of x equals x to the fourth times e to the negative x. So this is a similar example, and what we want to do here is find the derivative, and then look for where the derivative is equal to 0, because that's going to be where we find critical numbers, and then use that to break up a number line and find where our function is increasing or decreasing. So here, f prime of x is going to require the product rule. That's going to be 4x cubed e to the negative x, that's the derivative of the first times the second, times the derivative of the second, plus the derivative of the second times the first. The derivative of this is negative e to the negative x. So let's make that a minus instead of a plus. X to the fourth, e to the negative x. Or, if I do some factoring, x cubed e to the negative x times 4 minus x. Okay? And again, I want to set that equal to 0. Now we know that exponential functions can never equal 0. So if we're going to get zeros out of this, I need to look at the x cubed and the 4 minus x terms. That means that x will either equal 0 or 4 if I want this to equal 0. Okay, so now we're going to break up our number line using those values, 0 and 4. Once again, I have 3 subintervals. It's not always going to be 3. In different examples, you might find more critical numbers, which will break this up into more subintervals. That's just been the case with these last 2 examples. All right, and then as before, I want to plug some numbers into my derivative to determine whether the derivative is going to be positive or negative. So let's start with a number over here to the left of 0, which can be any negative number. What happens if I plug any negative number into my derivative? Well, let's use this form of the derivative since it's in factored form, which is easier to work with. A negative number to the third power is negative. E to any power is positive. And 4 minus a negative number would be like 4 plus a positive number. This must be positive. So I have negative times positive, which is negative. F prime is negative here. Now let's pick a number between 0 and 4. How about 1? If I plug a 1 in for x cubed, that's going to be positive. E to anything is positive. 4 minus 1 is 3, which is also positive. I have positive times positive, which tells me that we have a positive derivative. What if I plug in something greater than 4? Let's say 10. 10 cubed is positive. E to anything is positive. 4 minus 10 is negative. Positive times negative is negative. Okay? So again, if you forget what the first derivative test tells you about local max and local min values, you can just draw this little picture. Over here, because my derivative is negative, my function must be decreasing on this interval. It decreases, hits that critical number, and then over here, it's increasing. Here, it's increasing because my derivative is positive. We hit a critical number where we have a horizontal tangent, and then it decreases away. So I have a minimum here and a maximum here. Okay? I'm going to write local minimum of, we normally write the minimum first. I did it the other way around before. But let's plug 0, because that's where our minimum occurs, into our function. F of 0, which would equal 0. Okay? At x equals 0. Because plugging the 0 in for x here, when you're finding your minimum value, plug it into the original function. The purpose of the derivative is to tell us where we're increasing and decreasing and where those minimum values and maximum values occur. But the actual minimum and maximum are from the original function. So we have to go back to the original function here. Okay, what about my local max? That occurs at x equals 4. So f of 4, which would equal 4 to the 4th power, which is 16 times 16, that's 256, times e to the negative 4th power, which I leave in the form of that, e to the negative 4th. I'm not really interested in getting a decimal out of that, at x equals 4. Okay, these are the minimum and maximum values, not these. These are the critical numbers at which those minimum and maximum values occur. Okay, it's easy to get those mixed up sometimes. All right, moving along. We've done some work with the first derivative, but I did mention that we're going to use the second derivative here, and that's where we're headed next. So we've looked at the certain characteristics of graphs of functions, in particular increasing and decreasing behavior and how those relate to the first derivative. But another characteristic of a function is something that we call concavity. We say that a function, or the graph of a function, is concave up on an interval I if the curve lies above all of its tangent lines on that interval. And we say that it's concave down on I if it lies below all of its tangent lines on I. Now that may feel like a weird way of defining this, because you may already have a sense of what concavity is or what it means for something to be concave. But when we talk about something being concave, we're talking about an actual curving sort of behavior. So notice this function kind of curves in such a way that if it were like a bowl or something, then it would be opening upwards. You can kind of see that it's opening and that it's concave up here. A more obvious example is like an upward parabola. This is concave up because it's the where the bowl is oriented. Okay, concave down. Here's an example of a curve that's concave down, but a more obvious example would be something like a parabola opening downwards. These are both concave down. Okay, notice that this concave up function, if I pick any point and draw its tangent line, that's what these red lines are. The function is curving upwards away from each of those tangent lines. Notice this tangent line is kind of hard to see, but the red is actually below the blue except for the point where it's tangent. That's the point that those two things have in common. Everywhere else, it's the red line is below the blue curve. Similarly, a concave down function curves downward away from its tangent lines. That means it will lie below its tangent lines. So that's where that definition comes from. But intuitively, we think of it as opening up or opening down in kind of like a bowl or a curved sort of way. So here's a graph of a function that we're identifying concavity on different intervals. CD means concave down, CU means concave up. Now we can see in this function right here, it's concave down here because it appears to be curving downward this entire time. But then at some point between this part of the curve and this part of a curve, we go from concave down to concave up. And it's difficult to tell where it's happening by just looking at the graph. But you can kind of estimate it. This graph shows us where it happens at this value B, at this point B. But there is a change in concavity that happens here where we go to concave up. And then it's even harder to tell here, but you can kind of see by the way that this function curves like this to where it's moving, it appears to be concave down there. There's another point here where it switches concavity. Here we're concave up. We hit this point where the function appears to not be differentiable because it creates a cusp. But then after that, we're still concave up, and then we move to another interval where we're concave down. Okay, so that's just by looking at the graph. Now, we have what's called the concavity test. And this is what relates the second derivative of a function to concavity. The concavity test says this. If f double prime of x is greater than 0 on some interval I, then the graph of f is concave up on I. If f double prime of x is negative on an interval I, then the graph of f is concave down on I. And that this one's a little easier to remember because we oftentimes associate positive with up and negative with down. So it kind of fits what we imagine that to be. There is a proof of this in the back of your book in Appendix F, and I'm not going through the full formal proof. We could do that. It's just very time consuming. I would rather go with kind of an intuitive argument on this one. So returning to the these examples here and here. What we have here is a function that's clearly concave up because we can see its graph and we know that. But we've also defined concave up to mean that the function lies above its tangent lines on the interval where it's concave up. Now, think about this for a moment. F prime of x is the slope of any one of these tangent lines at whatever value of x would get us there, right? So when I'm talking about f prime, not f double prime yet, but just f prime, I'm talking about the slope of each one of these tangent lines. So what I'm seeing here, if I look at the slopes of these tangent lines as I move from left to right, the slope appears to be increasing. It's got a shallow positive slope here, a steeper positive slope there, and an even steeper positive slope there. So the entire time, the slope appears to be increasing. And the same thing would happen on this parabola as well. As I go from left to right, we have negative slopes, but getting shallower towards 0. That's increasing. The numerical value of those slopes are increasing. And then we go from a slope of 0 to positive and ever steeper slopes. That's the slopes are increasing that entire time. So another way of characterizing where a function is concave up is wherever f prime is increasing. F prime, which represents those slopes, is increasing throughout that entire interval. But according to our increasing-decreasing test, if a function is increasing, then its derivative is positive there. And what is the derivative of f prime? F double prime. Okay? If f prime is increasing on this entire interval, then f double prime must be positive there. That is an intuitive argument for why a positive second derivative would imply that a function is concave up. And again, you can formulate a very similar argument to say, that a function is concave down when f double prime is negative. So again, that is not a formal proof. That's not something that a mathematician would accept as proof, but it's a good intuitive argument that hopefully makes the case in your mind. All right. Now, another important term here is what we call an inflection point. So a point P on a curve y equals f of x is called an inflection point if f is continuous there and if the curve changes concavity there, meaning if it goes from being concave up to concave down or concave down to concave up. Going back to this graph down here, there are multiple points of inflection. Okay, that right there is a point of inflection. I'm just going to call it PI, point of inflection, because we change from being concave down to concave up. Notice the function is also continuous there. We have another point of inflection here, okay, because again, we have continuity at that point and we change from concave up to concave down. Another point of inflection here. The function is continuous there and we change from concave down to concave up. One important thing to note about this point, the function is not differentiable there because this curve forms a cusp or a weird corner there. Points of inflection do not have to be places where the function is differentiable. It only needs to be continuous there and change concavity. This point is not a point of inflection. It's not differentiable there, but that's not the reason why. It's not a point of inflection because we're not changing concavity at that point. We go from being concave up to once again being concave up. Here, though, we do have one final point of inflection because we change from concave up to concave down, and we do have continuity at that point. So that's what a point of inflection is. Okay? I think I'm going to do this next example on the next video.